Machine learning models rely on recognizing clear, distinct patterns in data. But in credit default prediction, those patterns are buried. Normal repayment data completely overwhelms the system, while the target event, the actual loan default, makes up less than 4% of the dataset. Finding these defaults is an extreme class imbalance problem. When you throw hundreds of financial variables at a model, the algorithms struggle to draw accurate decision boundaries through the high-dimensional noise. The standard engineering response to this noise is feature selection. We use mathematical filters like Select K-Best or Lasso to reduce the dimensions. These tools scan the dataset and keep only the variables that show the highest statistical correlation to the target event. But purely mathematical filters have a severe blind spot. In an extremely imbalanced environment, statistical relevance easily latches on to spurious correlations that heavily favor the majority class. The math optimizes for the massive cluster of normal behavior, missing the subtle signals of a default. Relying entirely on statistical distribution means the model is effectively blinded by the majority class. To build an accurate boundary, we need a different way to evaluate what makes a data point valuable. This gap in performance suggests we test a different filtering criterion, shifting away from purely statistical relevance and towards semantic relevance. Semantic relevance means evaluating a variable based on its real-world behavioral definition, rather than solely examining its numerical distribution in a spreadsheet. We are investigating whether large language models can leverage their massive pre-trained knowledge bases to perform expert-level feature selection through domain reasoning, challenging the effectiveness of traditional mathematical filters. This schematic maps a direct comparative experiment. Track A represents a statistical filter based on math. Tracks B and C represent LLMs selecting features logically. Both tracks feed their variables into the exact same random forest model for final training. If the random forest trained on the LLM-selected variables achieves a higher predictive score, it proves that injecting domain knowledge reasoning into the pipeline yields a stronger model than pure algorithmic optimization alone. The control group used a Select K-Best filter, which ranks features strictly by how much information gain they provide regarding the target variable. This chart details the resulting F1 scores. The mathematical baseline maxed out its predictive performance at a subset of 20 variables, hitting an F1 score of 0.68. For the experimental track, researchers prompted an LLM, specifically GPT-5, to act as a senior credit risk analyst. It was instructed to step through the variables and select them based on their financial definition and logical utility. The random forest trained on GPT-5 selections reached an F1 score of 0.70. It achieved a superior predictive boundary without performing a single mathematical calculation. Over 5 iterations, this prompting method returned a perfectly stable response, consistently outperforming the statistical baseline with 0 variance. The language model beat the math filter. To replicate this, we have to look closely at exactly how the data was formatted before it was given to the model. A common reflex in data science is to dump raw tabular CSV rows directly into an LLM, assuming that exposing the model to the granular data will yield the best analysis. This diagram outlines 3 distinct prompt structures tested to challenge that assumption. Type 1 provided the LLM with 0 raw data rows. Instead, it received natural language summaries containing basic descriptive statistics alongside translated column names. Types 2 and 3 progressively introduced samples of the actual training data, the raw tabular rows, into the model's context window. Across multiple test runs, feeding the raw tabular information actually lowered the F1 score and reduced the stability of the output compared to the natural language summary. Large language models have strict context window constraints. When forced to process brute force data dumps, they lose focus on overarching logical relationships. Curated semantic summaries, however, align perfectly with their core reasoning strengths. Pushing more raw data into the prompt does not yield better inference. To function optimally, LLMs require structural translation, not data dumping. So what exactly was failing inside the mathematical filter that the LLM managed to correct? To diagnose this, the researchers ran a permutation importance test. This technique shuffles a variable's data to measure whether that specific feature is helping the model's accuracy or actively harming its ability to generalize. This chart reveals the hidden failure of the Select K baseline. 10 of its mathematically selected variables returned a negative average importance. they dragged the model's performance down. Look at the LLM's permutation profile. It retained significantly fewer destructive features. The LLM's justification for selecting months since first vehicle purchase was based on its definition as a behavioral proxy for financial stability, reasoning that extends beyond the variable's numerical distribution. It also selected the KCB score, explicitly noting in its reasoning that the credit bureau score acts as a highly informative, orthogonal predictor relative to the other metrics in the dataset. The language model applies real-world logic to prune statistically tempting but logically useless noise features before they have a chance to poison the downstream model. This mechanism acts as a form of semantic regularization, a conceptual barrier protecting the model from mathematical overfitting. The LLM bridges the gap between raw data arrays and human behavioral reality. It processes variables as physical actions and financial decisions rather than abstract floats and integers. This pre-filtering provides the decision trees with a highly rationalized subset of data. With the noise stripped away, the trees draw cleaner, more accurate boundaries around the sparse default events. The LLM successfully categorized the data down into 3 distinct logical pillars: direct measurements of credit exposure, metrics of financial capacity and assets, and markers of behavioral proxies and stability. By shifting the burden of logical feature selection to a language model, the machine learning algorithm is free to focus entirely on what it does best: rigorous weight optimization. For data scientists and machine learning engineers, these findings offer a blueprint for modernizing pipeline architecture. Stop forcing massive tabular matrices into LLM context windows. The raw data dump degrades inference and wastes token space. Instead, implement a pre-processing translation layer. Convert your metadata, column descriptions, and basic descriptive statistics into clean, natural language summaries. Feed those summaries into your advanced reasoning models, dedicating the LLM strictly to the semantic filtering and justification phase. Then pass those selected features downstream. Leave the heavy numerical predictions and weight optimization to traditional models like random forests or gradient boosters. Building robust predictive models in highly imbalanced, complex environments requires pairing strict statistical rigor with deep semantic understanding.